Welcome to another Ostindo technical presentation. This module will take a closer look at the battery boost card. Let's start by taking a look at the main components. The blue component here is the crowbar SCR control module. This is just the mounting location for the control module. It is not electrically part of the battery boost card, merely a convenient place to locate the module physically. The P1 potentiometer is used to control the turn-off point for the battery boost circuit. The bridge rectifier here is really only used on DC trucks, so whilst it's still on the card, it performs no real function with the AC drive system. However, there is some current going through one of the diodes in the bridge rectifier due to the function of the SCR3 CM circuit. The Q1 and Q2 transistors are basically electronic switches and are used during battery boost control. The Zener diode ZD1 is part of the control circuit for battery boost. So let's take a look at the overall system schematic. Here we have the battery boost card as shown by the shaded blue area. The crowbar control module is not shown here because it's not part of the circuit electrically. The points shown here are the external connections to the card. This is the terminal strip that is at the bottom edge of the card. Starting from the top, terminal B provides the gate signal to SCR3, which is an SCR, inside the AFSE that controls actual battery boost current. Terminal C is the control signal to power the battery boost card. This is the high side driver from the 17FB104 card in slot 5 of the card rack. The signal is called AFSEL. The AFSELR pull-up resistor is tied to terminal H, as well as a low side driver from the 17FB104 card in slot 5 of the card rack. We commonly refer to this as the battery boost card handbrake circuit. Whilst there's a voltage on terminal H wire, the card is disabled. During battery boost, the 17FB104 card in slot 5 will take SCR3, CM low, and this will initiate the battery boost circuit function. Finally, this is the permanent ground connection to the battery boost card. Let's now have a look at the card connections in a little more detail. Here is the ground connection on terminal E. Here on terminal H is both the pull-up resistor connection and the low side driver connection from the 17FB104 card. This terminal has voltage applied to it by the pull-up resistor in most conditions. On terminal C, we have AFSEL, which is the switched 24 volt and part of sequencing. At the time of closing, the GFR relay and the GF contactor, we also have a 24 volt signal at terminal C to enable this card. Remembering though, the pull-up resistor on terminal H is locking the battery boost card in the disabled state. The final connection on terminal B is the gate signal to control SCR3. So, in summary, there will be a switched 24 volts applied to AFSEL on terminal C as part of the sequence closure, and there will be approximately 20 volts applied to terminal H almost exclusively, except during the transition of rest to ready. Let's look at the card in operation. The approximately 20 volts applied to terminal H will reach the P1 potentiometer, and this voltage will break over Zener diode 1, in turn supplying a voltage onto the base of transistor Q2, turning it on. Transistor Q2 will switch and instantly put a ground onto the base of transistor Q1. This will lock the transistor Q1 in the off state, effectively disabling the output of the card and therefore SCR3. Once sequencing is complete, the system will then take the wire SCR3 CM to a 0 volt potential via a low side driver on the 17FB104 card in slot 5 of the card rack. This removes the signal to the base of transistor Q2 and will turn Q2 off, which in turn will remove the ground to the base of transistor Q1. With the ground removed from the base of transistor Q1, a voltage will be applied to the base of the transistor via the R3 resistor. This voltage to the base of transistor Q1 will trigger the transistor, which will apply a gate signal to SCR3. And as SCR3 is forward biased, current should flow. Theoretically, the system will have 40 amps of battery boost current flowing in the alternator rotor, and this current will excite the alternator, producing voltage at the tertiary windings as well as the three-phase windings. Voltage at the tertiary windings will cause firing of the SCRs within the AFSE, and the output of the AFSE will cause voltage in the DC link to rise to 300 volts. Once the DC link reaches 300 volts, the battery boost card has completed its task and it is returned to the disabled state via the control of SCR3 CM. The low side driver for SCR3 CM will turn off, and this will allow the pull-up resistor connected to the SCR3 CM circuit to return the voltage at terminal H to approximately 20 volts. With 20 volts at SCR3 CM, the card will return to the disabled state where the voltage at terminal H is breaking over Zener diode 1 and is turning on transistor Q2, which in turn is locking off transistor Q1 with a ground connection, effectively removing any possibility of voltage at terminal B and turning off SCR3. The system will now complete VI testing and regulate the DC link voltage to 700 volts. This entire process takes approximately a second to complete and occurs each time the truck transitions from rest to ready. For further information on training and other services we offer, please reach out to the Ostindo team on 02-6574-9700 or via our website www.ostindo.net.au.